Question number 6. Another physical chemistry question. So you know this. XA solid and YA solids are two sparingly water soluble salts. So this is something related with KSP automatically tells the way. And they have given the solubility of XA is 2.01 grams per milligrams per decimeter. Then calculate the solubility product of KSP. So you need to find KSP of this XA. So these are just theory. So we will use the board very quickly. So I will check my screen. So they have given, so we have XA solid and its solubility is given as 2.01 milligrams per decimeter. So what you can do is you can calculate the molar concentration, molar solubility. Okay, they have given the molar mass of X, that is 110, and A is 40, so it is 150 basically. So how to convert this to MOL, dm minus 3? So 2.01 milligram, you can convert that to a gram by 10 to the power minus 3, and you divide it by the molecular weight, 150 grams per mole. Okay, so you will have this molar solubility as basically 2.01 over 150 10 to the power 3 mol dm minus 3. Then we need to consider about the equilibrium. So XA solid, I will now check the board. Okay, so XA solid will have X plus aqueous plus A minus aqueous. So this is how this solubility happens for this salt. And you know this 0 point over 10 to the power 3 mol dm minus 3. And this is the solubility of this amount will be soluble, which gives the idea. Same solubility of these two should be formed because the stoichiometry is 1:1. The anion and cation stoichiometry is 1:1. And you can apply the KSP equation for XA, and you can write X plus AQ concentration times A minus AQ concentration. So when you plug these two values here, because those two should be same now, there is no minus here. When you put here, it is plus. And you will see when you plug that values there. Quickly, I will tell that what is this value. And it will be 1.8 into 10 to the power minus 10. 1.80 into 10 to the power minus 10 mol squared dm minus 6. Okay, so this is a value that you should know. Okay, so this is done. Then this says a different story. So a completely water soluble solid NaA is added slowly to a 1 decimeter aqueous solution containing 0.1 moles of X plus and 0.1 moles of Y plus. So we have a 1 decimeter solution. Remember, all these are theory, okay? Don't forget to remember that. So what they are telling here is we have a 1 decimeter solution, okay? So we have a 1 decimeter solution where you have Y minus and X minus, and their concentrations are given. So 0.1 moles, and here also 0.1 moles. So you have 0.1 moles of Y minus and 0.1 moles of X minus. So very straightforward. And they have given the KSP of YA. KSP of YA as 1 into 10 to the power minus 7 m squared. That is YA. And we also found KSP of XA initially, it was 1.8 into 10 to the power minus 10 MQ. Right? So the first question is, predict which of the salt precipitates first. Okay. So clearly they say they add NaA. Right? Try to understand this. They add NaA. Okay. So when they add NaA, since you know the concentration of these Y minus and X minus, since the volume is 1 decimeter, the concentration is 0.1 m, 0.1 m for X minus and Y minus. Okay. They ask whether which one precipitate first. So you add A minus. So there will be this equilibrium that is happening. XA solid from X minus X plus AQ and sorry, A plus, wait a minute, is that given as X minus or Y minus? I have, yeah, that's cool, plus X plus and A minus AQ, and there will be this YA equilibrium that is happening, Y plus aqueous and A minus aqueous. Okay. So this is before precipitation. In fact, these solids are still like in the aqueous medium, right? But we need to find which one precipitate first. Okay. The simplest thing that you can tell here is you can find how much A minus concentration that is needed in order to precipitate either XA or either YA. Because you know the KSP value of these two. Here, these two are KSP values. So you can tell to precipitate the ionic product of either XA or YA should exceed their KSP value. Okay. So I can draw RQ, reaction quotient of XA, should be greater than or equal to KSP of XA in order to precipitate. So basically, RQ of XA means concentration of X plus AQ minus concentration of A minus greater than or equal to KSP of XA, which is 1.8 into 10 to the power minus 8 m squared. But in the solution, you know the concentration of X plus, which is 0.1 m. And you can calculate the minimum concentration of A minus that you need. Because when you do this calculation, you can calculate A minus concentration should be 1.8 into 10 to the power minus 10 m cube over 10 to the power minus 1, which is the X plus concentration is 0.1. So you can calculate according to this. A minus needed is 1.8 into 10 to the power minus 9. Okay, 1.8 into 10 to the power minus 9. And in the same way, you can calculate this for YA. So because here YA minus concentration will be given by 1.8 into 10 to the power minus 7 over the concentration is 10 to the power minus 1, 1.8 into 10 to the power minus 67. Okay, so you see here two values. Okay, what are the two values? In order to precipitate XA, you need a minimum A minus concentration of 1.8 into 10 to the power minus 9. And here you need 1.8 into 10 to the power minus 6. So which one is smaller? The smaller one is this one. Okay, 1.8 into 10 to the power minus 9. So when you put A minus here, initially it will reach this value 1 into 10 to the power minus 9. So when it reaches 1.8 into 10 to the power minus 9, XA will be starting to precipitate. That is the first point. Okay. Then XA will be precipitating out. Then when you add further, the A minus concentration in the solution will come to 1.8 into 10 to the power minus 6, because A minus concentration is constantly increasing. So at that point, YA is also starting to precipitate. Okay. So initially XA will be precipitating. Then when you add further, at this point where the concentration of A minus is 1.8 into 10 to the power minus 6, YA is also starting to precipitate. Okay, so that's the idea. So you can tell this story here. According to the KSP values, you can explain. This is another method that you can explain. Okay, so the next method is the KSP one, which I just told you. Since these two salts, the ions are in 1:1 stoichiometric ratio, like X plus A minus, Y plus A minus, you can even just compare these two KSP values as well to explain which salt precipitate first. For an example, you can just explain in this situation, since the KSP of XA is smaller than the KSP of YA, XA get precipitate first. You understand? Because when the KSP is smaller, you need very small amount of A minus concentration to pass this KSP value. So XA will precipitate first. You can straightforward directly tell that. Or either you can use this calculation where you can tell the ionic product of XA should exceed KSP. So to find the minimum A minus, you can show this A minus concentration for XA, and you can show the minimum A minus needed for YA. Then you can tell the minimum A minus needed to precipitate for XA is smaller, so XA will precipitate first. That's the idea. Okay. But you can use this straightforward method. You can tell the KSP of XA is smaller than KSP of YA. Therefore, this one will precipitate first. But don't forget, this KSP method is not always suitable. Okay? You can always use this method when your sparingly soluble salt is in stoichiometric ratio, the cation and the anion, when it is in the same ratio, you can use. For an example, 1:1, 1:1. So you can use for a 1:1 salt. But if this is like X2A instead of XA, so when you think about its solubility, this should be 2X plus A2 minus, and this will be Y plus A minus. So at this case, you need to understand the stoichiometry is not 1:1. This is not a 1:1 salt. Now this is a 2:1 salt with 1:1 salt. So you cannot compare KSP value of YA with XA at this point. So at this point, definitely you need to do this calculation and show A minus is smaller for one of these two salts. Okay, so get the idea. When the salt is 1:1 in ratio, you can compare the KSP value directly, which is in this particular question. You can directly tell since the KSP value of XA, since XA and YA is a 1:1 salt, so the KSP value of XA is smaller than YA, so XA will precipitate first. Or otherwise, you can show this calculation, find A minus and tell the story. Okay, but when you have a different salt, like 1:1 with a 2:1 comparison, you cannot just directly tell the KSP value is smaller, so it will precipitate first. You can't. You need to show this calculation and find A minus, and then you need to tell. Okay, so try to understand that concept. Okay, so this is what they have asked. All these are theory. Okay, so you should have learned in your theory class. So this tells predict which of the salt precipitate first. So they have given KSP of Ya this to compare. Okay. Calculate the cation concentration that remain in solution of the salt which precipitate first when the second salt begin to precipitate. So this is also again theory. We learned this in theory. Okay. So now you know okay. So you know for XA precipitation, A minus concentration needed was 1.8 into 10 to the power minus 9. So Y minus for YA, A minus needed is 1.8 into 10 to the power 6. Okay. So you add A minus. So initially it will reach this one and XA is precipitated. And you add further and further. Now when the second precipitation, which is this, when the second precipitation starts to happen, the concentration of A minus in the solution is 1.8 into 10 to the power minus 6. Okay, you cannot tell it is 1.8 into 10 to the power minus 9 because you add, and finally in the solution, the A minus concentration, when the second precipitation starts, it should be this value. Okay. Now they are asking when the second precipitation start, what is the concentration of remaining cation in the first precipitate? You understand this point? When you add A minus, the concentration of A minus increases. Now they are asking when the precipitation take place, the second precipitation take place, what is the remaining concentration of X plus? Because initially when this precipitation takes place, the A minus concentration was 1 into 10 to the power minus 9. So X plus also 1 into 10 to the power minus 8, 1.8. But when the second precipitation happens, the A minus concentration for this first precipitation also should be 1.8 into 10 to the power minus 6 m. Because this is the same solution. You cannot have one concentration for this A minus and one concentration for this A minus. Because solution itself contains all A minus, and this concentration, when the second precipitation starts, this A minus concentration should be 1.8 into 10 to the power minus 6. But don't forget, when the temperature is constant, they have to maintain this KSP value. So at this 1.8 into 10 to the power minus 6, they cannot have this same value as 1.8 into 10 to the power minus 6. In order to maintain the KSP, this X plus should have a different value. So you can put the KSP expression for XA now. You can write down X plus concentration, A minus concentration. So KSP is 1.8 into 10 to the power minus 10. X plus we don't know. That is what we have to find at the beginning of the second precipitation. But A minus we know at the beginning of the second precipitation was 1.8 into 10 to the power minus 6. So 1.8, 1.8, 1.6. So the X plus concentration, the remaining was 10 to the power minus 4. Okay. So when the second precipitation starts, you can understand the concentration of X plus at the end is 10 to the power minus 4m. Okay. So this was again the theory question. Okay. We calculate first which precipitate forms, and second, what is the remaining concentration of the cation when the second precipitate starts. Because when the second precipitate starts, A minus concentration is common for this equilibrium and this equilibrium. So it should be like 1.8 into 10 to the power minus 6. And if you know this is 1.8 into 10 to the power minus 6, KSP should be remain constant. So in order to make this KSP remain constant, this X plus concentration should change. And we have calculated that as 10 to the power minus 4. Okay. So did you get that? So did you get that point? That's good. That is very important to know. So I will share again. So we have done this one, so that is done. So part B. So again, remember these three A, B, C, all are just mostly theory. That is important to understand. Okay. So when a weak acid HA is titrated with a solution of Na, so we have HA in our let's say the titration flask, and we are titrating this with NaOH, which is our base. Okay, we are going to titrate this with NaOH, considering the hydrolysis of A minus. Show that the pH of the solution at the equivalence point. Okay, so equivalence point means 1 mole of this reacting exactly with 1 mole of NaOH. You need to show the pH is this. And you also given pH plus pOH is pKw, which you should know, and pK plus pKb is pKw. So you also should know. You know Ka times Kb is Kw. So based on that, this relationship is taken, and Kb is this they have given. So we don't have any problem of determining this. So we will see how we can follow this. Okay, so we have HA reacting with NaOH. So it will basically form Na plus water. Okay, so at equivalence point, there will be no HA or no NaOH. There will be only Na. So since Na is a salt, it will form Na plus and A minus. Okay, and this A minus, it will not remain as it is since it is a salt. It will hydrolyze, forming HA and OH minus. Since it gives out OH minus, so this should be a Kb expression. So Kb is equal to OH minus concentration times HA concentration in this case over A minus concentration. Okay, this is already explained in the description as well. Now, what they are telling here is to find the pH of this and give that as the expression that they have described. So since this is hydrolysing, it shows hydrolysis here. So if the concentration of this at the beginning was C, here C, 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 C. So you know this should be C minus X, and this is X, this is X. So in principle, you can understand here, instead of HA concentration and OH minus concentration, I can directly put OH minus concentration squared because these concentrations are same. Okay, so my Kb expression becomes OH minus squared over A minus. Okay, so now check the relationship that we have, because we have given many relationships. See, pH plus pOH is equal to pKw, pKa plus pKb is equal to pKw, and Kb is already given, so we know that. We determine that Kb. What is Kb here? So I can simplify here. OH minus concentration squared is equal to Kb times A minus concentration. Okay, then what I can do here is make this as pKb, or let's take this as POH in fact. Okay, so how can I take this as POH? So the simple thing is that you can take the root here. So you will have OH minus concentration. Then you can take minus log base 10 OH minus concentration, which will be my POH. Okay, and here there will be Kb times A minus concentration to the power half, and then you need to take log base 10. Okay, so I will erase all these. So I have POH minus log 10 Kb times A minus half. Okay, so POH is equal to half. I can take in front, half log Kb minus half log A minus concentration. Okay, so this could be POH. This is half minus log Kb is pKb minus half. In fact, I will put half in front and minus log A minus. I will keep it as it is because it is in this expression. Because when you check the expression, I will show you the expression. You have to show this as this one. So we have already this one. Okay. In our expression, we have already that. And we have to just change these two. For that, we have this expression. You see this? Because POH can be written as pKw minus pH, and half into pKb can be written as pKw minus pKa minus half log A minus concentration. So this is straightforward, right? So at the end of the day, I will again stop sharing to show this one. So we have obtained up to this one. And instead of POH, I can put using this one. POH will be equal to pKw minus pH. And half into pKb can be written as pKw minus pKa. Okay. So here, if I remove the bracket, there will be a minus pKa half. So I can cut this one, cut this, and put half pKw minus pH is here. And there will be half pKa, half log A minus concentration, and you can rearrange this to get pH expression will be half pKw minus half pKa minus half log A minus concentration. So this is the expression that they have expected from you. This is just mathematics, okay? You just have to write down OH minus, then get the root and rearrange, that's all. If you are not good in mathematics, please go through this, okay? Very important. So this is the first one. And calculate the pH at the equivalence point when a solution of 1 into 10 to the power minus 3 of HA is titrated with 1 into 10 to the power minus 3 of OH minus. So the idea here is why they have given the concentration of HA and OH minus is to know at the equivalence point there is only A minus according to the stoichiometry 1:1. So when you have this at the equivalence point A minus, you are reacting 10 to the power minus 3 of this one and 10 to the power minus 3 of this one. So finally, what should be the concentration of A minus that is formed? It should be 1 into 10 to the power minus 3. Okay, so you know the concentration of A minus. So according to our equation, we need to find pH. So half pKw, you know, at 25 degrees Celsius, Kw is 10 to the power minus 14. So half into 14 here plus half pKa. So they have given Ka 1 into 10 to the power 5. So basically, if you find pKa, it will be 4.76, around 4.76. So you know 4.76 now here. And there is the final one, which is plus half into log A minus concentration. To find A minus concentration, this detail is given. Okay, so you can put here 10 to the power minus 3, and you can find, but don't forget the volume is doubled. Okay, because when you titrate this same concentration with the same concentration, you need to add V volume here, and there should be V volume here, and finally this should be 2V. So you have to first divide this concentration by 2, the final concentration, because if I show you that, because this is the concentration, so you are adding 10 to the power minus 3 m, 10 to the power minus 3 m, but you need to multiply it by the same volume to get, in order to have the equivalence point, same amount of NaA form. So basically it will form 10 to the power minus 3 m say concentration, but the volume is double. Okay, so this will be like 5 into 10 to the power minus 4 m, right? So when you find the pH will be around, where is the pH? 7.69. Okay, that is important to mention. So the pH was 7.69. So it is correct. Why? Because you are performing a weak acid strong base titration. So at the end, at the equivalence point, you have only the basic salt, which is from mainly derived from the strong base. So basic salt gives you OH minus in the equilibrium. When we perform this hydrolysis, OH minus is given out. So OH minus is given out means in the equilibrium, the salt hydrolysis of A minus. So this is from the HA and OH minus. The effect of OH minus is greater. Why? This is originated from NaOH. So this gives you a positive feedback for your pH. So that is why this is little bit basic in nature. Okay. Right. So I will share the screen again. Where is it? Okay. So we can calculate pH. So that is done. And the next thing that they tell is a 500 cubic centimeter solution of 2 into 10 to the power minus 3 Y plus, okay, is added to 500 cubic centimeter of 2 into the power minus HA. Solid Na was slowly added to this solution in order to precipitate Ya. Okay, calculate the pH of the solution when Ya begins to precipitate. So this is again a theoretical one. Okay, so we will draw the description and everything. First, I will draw the information. So we have Y plus 500 cubic centimeter of Y plus 2 into 10 to the power minus 3m, and this was added to 2 into 10 to the power minus 3m of 500 cubic centimeter of let's say, what is it, A minus maybe? Yeah, it was HA. So we have Ya precipitate that we can expect to form. So we can expect that Ya is formed. Let's say Ya solid is formed. We don't know whether it is happened. So then they add solid NaA. So which gives you the idea. Initially there was no precipitation, but when they add NaA, they see precipitation, and the KSP of Ya is also given. It was 1.10 into 10 to the power minus 7m. So we knew that already in the previous question, right? So what they are telling, find the pH of the solution when the precipitation happens. Okay. The first thing that you need to understand here, the concentration of Y plus and HA when they are mixed, because the volume is doubled with the same concentration. They are adding 2 into 10 to the power minus 3 and 2 into 10 to the power minus 3, but when they add, the volume is double, right? So basically the concentration of HA is something like this, 10 to the power minus 3 m times 500. Now the volume is 1000, which gives you the idea the concentration becomes half. So basically, initially, this concentration will be 1 into 10 to the power minus 3. This will be 1 into 10 to the power minus 3. Okay. And then they add an A in order to precipitate YA. Now, again, rethink. In order to precipitate this YA, what should be the concentration of A minus that should be given from this HA? That is the thing that you need to understand. Okay, because you know there is a concentration of 1 into 10 to the power minus 3 of Y plus in this solution. What should be the A minus concentration that should be present in this solution when there is this precipitation happening? You have the KSP value. So this is equal to Y plus aqueous concentration times A minus aqueous concentration. So what is the concentration of Y plus here? Concentration of Y plus, you mix it. So actually what is forming when you mix this one, there will be some H plus that is forming, and there will be YA that is forming. Okay. And when you mix, you know the concentration of Y plus should be half because of the volume doubling. So it will be 1 into 10 to the power minus 3, in fact. So I will quickly check this one. Okay. So wait for a while. Right, so the idea is same, that you know this Y plus is 10 to the power minus 3, KSP is there, you can find A minus. So if you think that A minus is that amount, you can even find the concentration of H plus that should be given when the acid forms. Okay, for an example, now this is 1.8 into 10 to the power minus 7, Y plus is 10 to the power minus 3. So you can find A minus concentration. So it will be 1.8 into 10 to the power minus 7 over 10 to the power minus 3. So this will be 1.8 into 10 to the power minus 4 m. Okay. So in this HA equilibrium, because this A minus should be given by this HA in order to form this precipitate. So HA should be in equilibrium with its H plus and A minus. Okay, so that's the idea. So you know the initial concentration of HA again. So this is 1.1 into 10 to the power minus 3. Should form like minus X when it reacts. And this should form X, and this should form X. In fact, if you think in that manner. Okay, so A minus, you know, it is 1.8 into 10 to the power minus 4 m. But your H plus value cannot be the same value. Okay, because in order to maintain this Ka value of HA, this should change. Because this A minus is only in the case for the precipitation. So when the precipitation starts, this A minus is this. So as this A minus is this. So if your Ka expression is considered, it will be H plus concentration, A minus concentration over HA concentration. So Ka is 1.8 into 10 to the power minus 5. H plus you don't know, you need to find it. A minus is 1.8 into 10 to the power minus 4. HA is 1 into 10 to the power minus 3 minus x. So we can neglect x. So this will be minus 3, 1 into. So you can cut 1.8, 1.8. And there will be minus 1 here. And H plus concentration will be 1 into 10 to the power minus 4 m, where your pH then will be 4.00. Okay. So this is the calculation for this. So what is the idea? You first find the amount of A minus in the solution. that necessarily need for this precipitation to happen. So for that, we use the KSP expression with Y plus concentration that is calculated here after the mixing of this solution. And then you know the A minus concentration, which was 1.8 into 10 to the power minus 4. But how this A minus form? Because of this mixing. So in the mixing procedure, to Y plus to be get combined with A minus, this A minus should be given from this HA. So HA is in equilibrium like this. So in normal equilibrium, when there is HA 1.1 into the power minus 3, it will react X amount will be forming, and X amount will be forming A minus. But don't forget, this is in normal equilibrium. But here there is Y plus, where this X plus some amount of A minus can be reacted. This is the reacted amount. So we have found the reacted amount, and now we need to find how much X, it means how much H plus now in present in the new equilibrium. This is just if you have HA in the solution, XX. But when you have Y plus, now this cannot be XX. This is something else, and this is something else. And we found that this is 1.8 into 10 to the power minus 4. And X, which is this H plus concentration, was 1 into 10 to the power minus 4. So at the end, you can imagine this was 1.8, this was 1. Different. Why it is different? Because they have to maintain this Ka value. Because it is also a equilibrium constant. Okay. Right. So I will share the screen again. So this was the last part. So that is also done. Right. So we have to move to the last section of question number 6. Right. So we have a solution. Now, see, this was related to KSP. This was related to ionic equilibrium, plus the last question is somewhat little connected to the KSP and ionic equilibrium. And then they are coming to the phase equilibrium. Okay. So benzene and toluene. So you know what is benzene here? So benzene is the normal benzene. And toluene is benzene attached monosubstituted with a CH3 group, alkyl CH3 group. So mix completely with each others, yes, to form the binary mixture. The boiling point of benzene and toluene are 80. So benzene, the boiling point is 80. Toluene, the boiling point is 110. Okay. Draw an appropriate temperature composition phase diagram for the above system. So I will stop share and use the screen here again, just to make sure everything right. So the idea is, so we have benzene, which is 80 degrees Celsius, and we have toluene, which is 100 degrees Celsius, right? 100 or 110? Yeah, it was 110. So it is expected, right? Because you can see these two are very similar molecules, but you can imagine the molecular weight is little high. So since the molecular weight is little high, the boiling point should be little high. That is why this is high. Okay. So they are asking for a temperature composition. So what do you think? So we will draw a temperature composition. So you need to mention temperature, degrees Celsius. You need to name all axes. That is very important. And I will mention here X benzene is equal to 0 and X toluene is equal to 1. And here you need to write composition change. Composition. XB is equal to 1 and X toluene is equal to 0. Okay, you have to mention XB is for mole fraction of benzene, XT is mole fraction of toluene. Okay, now we need to put the temperatures. So what is XT is equal to 1 means you have only toluene. So when you have only toluene, your boiling point will be 110. Okay, and when you have benzene, your boiling point will be 80 degrees. So that's the idea. Okay. Then you have to explain that composition. So when you change from benzene towards toluene, your boiling point is increasing. So should increase. Sorry. And when you go from toluene to benzene, your boiling point is decreasing. So it starts to decrease like this. Okay. And remember, this is the liquid phase, this is the vapor phase, and this is where the liquid vapor equilibrium presents. Don't forget to mention all these things. So you have to name the axes, 1 point, put the values, 2 points, mole fraction values, 3rd point, show the equilibrium, that is 4th point. Okay, so everything should be included in the phase diagram of a composition and temperature. Right, next question. Draw an appropriate temperature composition diagram for the Bohr system. Yes, done. Consider a distillation of a liquid mixture of P. What is P? So we have a mixture of P with 30% of benzene. Mark the boiling points of T1 of liquid mixture P on the phase diagram above. So now they are telling we have a liquid mixture P with 30% of benzene. So according to our diagram, okay, so where is the mole fraction of benzene? That is 1. So here you have benzene 1. So 30% means, now this is around 50% of toluene, 50% of benzene. So here we have to divide this by 5, around 5 parts. 40%, 30%, 20%, 10%. So they are asking a position around this. So what is the composition here? Here you can see there is 30% of benzene and 70% of toluene. So this is the liquid mixture P. Okay, so you don't need to mention those things, just to explain for the explanation. Okay, so what they have asked, that is important. Mark boiling point T1 of the liquid mixture P on the phase diagram above. So you need to mark the T1. So what is T1 here? So this is the place that you need to show here. And at this time, your boiling point T1 is this. This is T1. It should be little it should be shown a little different. So I will just show clearly. Let's say 30% is around here. So this is T1 that you have to mention. This point, okay? And they say mark the composition Q of the vapor phase at T1 on the phase diagram of this one. So it should be, you should understand the process. First, I will explain what is actually happening. Okay. So you have a mixture. Okay, this is normally called the process of fractional distillation. But again, these are theory, okay? So when you have a mixture, where there are two compounds with different boiling points, you can do fractional distillation and separate one compound. So they are doing for this type of a mixture where you have 30% of benzene and 70% of toluene. What you normally do is you heat the mixture. So there will be a liquid composition like this initially, then you heat it, and then this will be vaporized through the liquid vapor equilibrium to this direction horizontally, and then you cool down and you will have the liquid vapor composition Q here. This will be your Q, where you have more benzene. You see why more benzene? Boiling point of benzene is lower, and you need to understand its volatility is high, so it will go more when you heat here. So in the final composition here, after one cycle, we say this is one cycle: heating, equilibration, and condensation. So this is one cycle. So if you start from here, you will have like, if you start from this composition, you will just heat it, do it, heat it, do it. So there will be two cycles to reach around the maximum purity. Okay, so here you heat, and there will be liquid vapor equilibrium at this boiling point, which is called T1, and then you condense, which drops the temperature, and there will be this new composition of the vapor. This is composition of the liquid where you had only 30% of benzene. But here when you do the more important things, then it will increase. Okay. In fact, we should have started from here because benzene 30% is here. So here, 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 here. So this is how it should go, right? So because here it is 0, so 30% is here. You heat it, equilibrate, you condense. So here it should be the Q. Okay, because here it was 70% of benzene. But in the question it says 30% of benzene. So it should start from here. Right, so this is very important. So first know how to draw a temperature composition diagram. Label axis, put the mole fraction, put the boiling points, show the curve, show the vapor equilibrium, show the liquid equilibrium, show the liquid vapor equilibrium at the middle. That's first point. Second point, they say they use a 30% benzene mixture. So you start from here, this is the liquid composition. Then you heat. When you heat means there will be vapor coming out, more benzene coming out. So because boiling point is lower, mean volatility is high. So there will be a liquid vapor equilibrium at this boiling point. So this should be T1 here. Okay, because we started from 30%, it was here. And then you condense. When you condense, the vapor composition is this. So you can imagine when you start the liquid, there was here the benzene composition. But when you heat and condense, your composition is here now. So the vapor has more benzene and the liquid mixture has more toluene. Because more benzene will be evaporated to the vapor, more liquid will be present with toluene. So when you do this one cycle, there will be like around 60% purity of benzene, and you can do another cycle and you can get closer, 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 and finally, when you do several cycles, one cycle, two cycle, maybe three cycle at the end, when you do several cycles, finally you will get pure benzene. That's it. Okay. So did you understand that process of fractional distillation? So this is normally called the fractional distillation. So when you have crude oil with different hydrocarbon chains like petrol, propane, butane, LP gas, all those are obtained using fractional distillation. Because based on the carbon number, when your molecular weight increases, the volatility of the compound decreases. So initially when you heat, low molecular weight volatile compounds comes out. Okay, so that is the way it happens. Okay, so did you get this process? That's good. You say yes means that's good. Right, so I will share the screen again. So this is done, this is done. Explain qualitatively the difference in composition between the liquid and vapor phases at the temperature T1. Name the technique which is used to separate benzene from the above binary mixture. So the technique was fractional distillation, and explain qualitatively the difference in composition. So the difference in composition is you have to mention in the vapor phase, there will be more composition of benzene than toluene. That's it. Very simply. You don't need to explain many things. You have to just tell the simple basic thing. The composition of the vapor is higher with benzene and than the toluene, and in the liquid it's the other way around. Okay. Last one, draw the temperature composition phase diagram for a binary mixture formed by two miscible liquid with equal boil. This is very important. So equal boiling points. So you can draw all same axes. Nothing is going to change. Temperature in degrees Celsius, composition of, let's say, A and B. In A and B composition, but when you mark boiling point here, you will mark like, let's say, TA, T naught A, in fact, the boiling point. Here you will have T naught B, the same boiling point. Okay. So if there is a change in boiling point like this, you can use fractional distillation to extract one of the compound using this fractional distillation method. But when you have same boiling point, think you boil it, same compounds will evaporate and there will be no difference in the liquid vapor mixture, because your liquid is, let's say, here, you heat it, both will be evaporating at the same temperature, and when you condense it, both will be there at the same composition because the boiling point of both are same. So at the end of the day, when you try to separate these, you will not have a curve like this, separation from the liquid and the vapor. There will be a curve like this. Okay, this is T naught B, this is T naught A. Since the boiling points are same, you will have just a single line because there is no variation in the liquid or either vapor phase because boiling points are same. So you will get a single line like this. Okay, so knowing this is enough because I cannot explain more and more because this will make your life harder and harder. So this is also a nice question.